Welcome, everybody. So my name is Laurent. I'm the room manager for this session. And today we are welcoming Eric and Gira from NVIDIA, who will talk about how to accelerate Spark Connect by using GPUs. Guys.
Thanks, Laurent. Hello, good morning. Welcome to our presentation on GPU-accelerated Spark Connect. My name is Ger Shigalov. I am with the Spark ETL team at NVIDIA, and my co-presenter is Eric Ordentlik, who leads our sister team for Spark ML at NVIDIA. This presentation is the result of the collaboration of our teams and the wider Spark community. Per usual, a couple of formalities. First, an acknowledgement the presentation may contain forward-looking statements. Next, a quick reminder to provide feedback for every session you attend, including this one. It can be done either through the app or on the web in the attendee portal. Our agenda today includes a brief introduction and background with motivation for GPU acceleration and the Spark Connect, and show how Spark Connect can further simplify access to GPU acceleration in Spark SQL and Spark ML context. We conclude with presenting some benchmark results and a recorded demo. Feel free to catch us in the hallways to see a demo live on the laptop. One reason we need scalable distributed systems like Spark is that data is growing rapidly. IDC Global Datasphere 2023 says that the amount of data is growing at a compound annual growth rate of 28% per year. Hundreds of zettabytes of data are generated each year. How is compute going to keep up with this growth? We believe the answer is to GPU accelerate batch computing workloads, and specifically Apache Spark. So how do we get there? Spark 3 enabled some key functionalities. The first was columnar processing, which is much more efficient for data processing than a row-by-row approach. The second was the ability to schedule tasks on resources such as CPU, FPGA, or other type accelerators like a GPU. A third was a plugin interface to allow alternative SQL execution engines. These innovations made Rapids Accelerator for Apache Spark possible. It accelerates Spark SQL and DataFrame operations using NVIDIA GPUs. It works with various Spark schedulers, standalone, Yarn, Kubernetes, and the best part, there is no code change required. It is integrated with a number of Spark distribution and cloud service providers, as you can see on this slide. A small selection of it. So the plugin builds on top of NVIDIA open source project called Rapids, libqdf specifically, which is a DataFrame library built for GPUs, and it's a native library in C++. We integrated via JNI. More recently, the Spark accelerator for Spark has been extended to also accelerate Spark's MLlib API. This part of accelerator is a Python library built on top of the Rapids project called QML. The Rapids accelerator for Apache Spark for both ETL and ML is open source. You can find it on GitHub. The links will be provided at the end of the presentation. And you can download binary artifacts like jars and pip packages from Maven and PyPI repositories, respectively. Meanwhile, Spark Connect was introduced in Spark 3.4 and provided a way to run Spark SQL and DataFrame application over lightweight gRPC protocol. It included necessary protobuf definition and client and server code for executing these interactions with the Spark JVM runtime on the server side remotely. Spark Connect decouples the application code from the runtime with very lightweight client or application-side libraries, and enables easy implementation of new language bindings in languages like Go, Swift, or recently proposed Rust, and makes maintenance of Spark versions and client applications much more manageable. A key innovation in the just released Spark 4.0 is the extension of the Spark Connect protocol to cover Spark MLlib functionality. Applications running over Spark Connect can now, with Spark 4.0, include Spark MLlib invocations, in addition to the originally supported SQL and DataFrame operations. For now, ML over Connect is supported only in Python client, via the familiar PySpark.ml API, but other language bindings should be possible. So the tremendous standalone benefits of GPU-accelerated Spark and Spark Connect, respectively, strongly motivate enabling GPU-accelerated Spark SQL and ML over Spark Connect, the details of which are the main topic of this talk. As shown on the right of this figure, the basic idea is simple and involves replacing the baseline CPU-based Spark operations invoked by the Spark Connect server with the GPU-accelerated ones. In the rest of the presentations, we'll explain how and why this works for both SQL and ML, explain key Spark 4.0 innovations that enable the ML part of this. We delve into service provider deployment and conclude with some benchmarks and an end-to-end demo of GPU-accelerated Spark Connect for ETL and ML together. So before diving deeper, let's recap the benefits of Spark Connect with GPUs. We decoupled apps like notebooks from heavyweight dependencies such as Spark itself, Rapids, and CUDA, and retaining the familiar Spark user-land API. Clients and Spark runtime side no longer have to be upgraded in lockstep. So now let's take a look at the lifecycle of a query executed over Spark Connect. So the execution of Spark SQL and DataFrame-based applications. On the left is the client running some simple SQL and DataFrame application code. The application, which is pure Python in this case, or a Jupyter notebook, first connects to the remote Spark Connect server. So the flow goes from the left to right. When executed on the client side, the Spark Connect converts each Spark SQL query to an unresolved logical plan, which is in turn sent to the server over, as a gRPC request. On the server side, the logical plan is resolved into an analyzed logical plan, then optimized, and finally converted to a physical plan. A tiny snippet of the physical plan in this example is shown in the light blue shape. So somehow the optimizer turned this count query over join into a hash aggregate. So what happens when we introduce Rapid Spark? The accelerator is able to plug in on the server side at the physical plan level, take in an input that is a CPU plan, and transform it into a GPU-accelerated plan. Note that the CPU executes in a row-by-row basis, represented internally as an RDD of internal row. The Rapids accelerator instead executes at the column level, which is implemented internally as an RDD of columnar batch API. Otherwise, the physical plans are equivalent, with the execs and operators being replaced by GPU equivalents. So this is what's happening under the hood. Everything else is using Spark. Task scheduling and parallel execution is driven as usually. The client-side application code is exactly the same, no changes required. So that's why we want to have as little green on the left-hand side where the client code lives, and as much green on the right-hand side where the execution is accelerated. And I'm handing it over to Eric to walk you through the Spark ML part and the rest of the presentation.
Okay, thank you, Gar. Good morning, everybody. Actually, let me just rearrange this a little bit. So I can... Okay. All right, so now that we've heard about how Spark SQL and its acceleration work over Spark Connect, let's take a look at how things look for the ML side of things. So here's CPU-based Spark ML over Spark Connect that was recently enabled in Spark 4. So on the left is a simple Spark ML application that reads in some data from a Parquet file and invokes the fit method on the k-means estimator to do some clustering. The execution of the application code, as in the non-ML case, computes an unresolved logical plan to represent the data feeding into an ML action. In this case, it's k-means fit. And the plan and the ML parameters, including the algorithm and the action being invoked, are serialized and sent via the gRPC protocol to the server. The server side then deserializes the client's messages and resolves the logical plan into a data frame, along with the Spark MLlib classes, methods, and parameters that were specified in the messages. In this example, the fit method is invoked on the k-means estimator class on the resolved data frame, and its execution just follows or is carried out by the baseline classical Spark MLlib implementation. The resulting model after the fit method completes is cached locally on the server side, and an ID identifying this model is returned to the client to allow it to possibly remotely invoke methods on the model, like transform, for example, or extracting and downloading the model coefficients for saving locally on the client. Okay, so let's look at the accelerated case. In this case, the Spark Connect server is now attached to a GPU-accelerated Spark cluster, similarly to the accelerated SQL case, while everything else stays the same, especially on the client side, just like in the SQL case. So in other words, no application code change is needed, and moreover, the messages flowing back and forth between the client and server are unchanged as well. To leverage the attached GPU-accelerated Spark cluster for ML on the server side, there's a plugin mechanism that can be specified to replace the baseline Spark ML functionality and with accelerated counterparts. And the materialization of the data frame to be used in the ML computations leverages all the accelerated physical plan execution engine by the Spark Rapid SQL plugin as before. So now that we have a basic understanding of how GPU-accelerated Spark Connect works from the application user point of view, let's look at deployment from the service provider point of view. Oops. So one way to deploy a Spark Connect server is to use a shell script that's conveniently included in the Spark distribution. So here's an example invocation for starting a CPU-based Spark Connect server connected to a standalone Spark cluster, the master node for which is specified in the URI in the -- master argument here. The same script can actually be used in the case of GPU-accelerated Spark Connect, but with some additional GPU-related configs, as shown here. The new configs in the GPU case are highlighted in dark green. So first, notice that we're specifying 2 jars for Spark Rapids ML and SQL acceleration, respectively, along with some configs specifying the plugin classes in these jars to invoke for, respectively, accelerating the SQL part and the ML part. Finally, we have some GPU resource-related configs, and these go back to Spark 3, as Gara mentioned. And not shown are possibly additional configs that control the behavior of the ML and SQL plugins. So now that we have an idea of how GPU-accelerated Spark Connect works and is deployed, let's take a closer look at the innovations in Spark 4 that enabled ML over Spark Connect in the first place, and then the acceleration thereof. So basically, it made sense with that foundation to talk about acceleration of ML over Spark Connect. So roughly, here's the state of Spark Connect before Spark 4. So there was built already as of Spark 3.4, there was only built-in support for Spark SQL and data frames, with protocol buffer message definitions for conveying SQL plans and commands, along with server-side code for handling the corresponding requests, leveraging core Spark SQL for the actual execution. In case it wasn't clear before, the partially green Spark SQL block on the server side in this figure denotes the fact that the Spark Rapids accelerator for SQL could actually interoperate with Spark Connect, even before Spark 4, since its implementation is at the physical plan level and below, and thus kicks in fully on the server side. Spark 4 developers then went on to extend the Spark Connect protocol to cover essentially all of Spark MLlib functionality. This involved defining new messages to convey ML relations like model transforms, as well as ML commands like the fit command for Spark ML estimators. The Spark 4 PySpark client includes all the functionality needed to serialize, deserialize the new messages based on application code, and also the server response that comes back after the execution. On the server side, a new ML handler was added that converts the decoded ML protocol messages into Spark ML library invocations, and also added, but not shown here, but was shown earlier, is the model cache. Okay, so finally, Spark 4 developers also added an ML backend plugin interface to allow the ML handler to instead invoke alternative implementations of Spark MLlib functionality, which in our case, leverage GPU acceleration. Here is the ML plugin interface definition. As you can see, it's pretty simple with only one method that converts an input MLlib class name to a plugin supplied alternative. And here's a portion of our specific Spark Rapids GPU-accelerated ML plugin. You can see at the top the mapping of baseline Spark ML logistic regression class names to their Rapids accelerated counterparts. The heavy lifting is done in the partially shown definition of these alternative classes that actually implement the plugin logic. So in this case, the ones corresponding to logistic regression. The full plugin implementation has other mappings and alternative algo implementations for the ones we support. The only requirement on the plugin implementations is that it can be invoked from Scala and Java. In our case, this initial Scala invocation actually hands off the full implementation to a Python C++ library that connects back to the Spark Connect Java process via Py4j, all on the server side, to carry out the actual computations. So let's change gears a bit and recall why we're talking about GPUs in the first place. And it is, of course, all about the benefits of faster and cheaper processing. And with that, I'm going to share some benchmark results that are similar to ones that we have shared before for ETL processing and ML. So the first benchmark is for Spark SQL DataFrame processing and is called NVIDIA Decision Support, or NDS for short. It's a slight adaptation of the TPC-DS data processing benchmark widely used in the industry. However, we stress that we're in no way claiming NDS-related results as official TPC-DS results, as they do not comply with the latter's full specification. You can find the details of the NDS benchmark, like how it differs from TPC-DS, along with code to generate the data for it and run the queries in the GitHub repo shown at the bottom of this slide. This slide has details about the Spark Yarn clusters, CPU and GPU, that were used to obtain the results I'll show in a bit. These clusters were deployed on EC2 instances depicted in the table, 8 instances in both the CPU and GPU cases. The GPU instances each had one NVIDIA L4 GPU. We ran the NDS benchmark at the 10K or 10 terabyte scale factor with the data stored on HDFS running on these nodes. These are some of the configurations provided here mainly for future reference by folks that might be interested in reproducing the results. These have been tuned to respectively optimize CPU and GPU benchmark performance. This includes configs specific to the Rapids accelerator on the right, like specifying the plugin class, a shuffle manager, and sizes of various GPU-related buffers. So here are the results. The plot on the left shows running time in minutes for the CPU and GPU clusters in blue and green, blue for CPU, green for GPU, respectively. And the plot on the right shows the respective compute costs. We see that the GPU cluster was about 4.5 times faster than the CPU cluster and about a quarter of the cost, as measured by the EC2 instance cost per hour multiplied by the running time. The cost savings comes from the much shorter running time, despite somewhat higher per hour cost for the GPU cluster. For the ML speedups, here's some somewhat less formal benchmark results, again similar to ones we've presented previously. This time we ran our standard suite of ML estimator fit method micro benchmarks, which can be found in our GitHub repo shown on the slide, for the Spark ML algorithms that we currently accelerate. And we did this on an in-house server that had multiple A100 GPUs, and we used 2 of them for these results in each case of each algorithm. And this was run over Spark Connect with Spark 4 using the Rapids accelerator for ETL and ML. The only ETL in this case, though, is reading Parquet format and also converting from array type in the format to vector type. For the CPU side, we had 16 cores per GPU, so a total of 32 cores. The blue and light green bars show execution time in seconds for the CPU and GPU cases respectively. And as you can see, there's anywhere from 2x to nearly 70x speed up depending on the ML algorithm. And notice that the y-axis is log scale, so these are somewhat compressed. The variation in speed up depends on how much compute to I/O there is for the individual algorithms. And k-means in particular is a particularly standout one from this point of view. The algorithm parameters and data dimensions were selected to be fairly high compute regimes to highlight benefits of GPU acceleration. Let me talk a bit about the dark green bars. So this is performance that would be possible if either some code change was allowed for the GPU acceleration case or if we extended the plugin to not fall back when handling certain steps related to vector data type. So if either of those two were addressed or possible, we would be able to achieve the faster execution time for these benchmarks shown by the dark green bars. Okay, so with that, we can move on. We're going to move on to a demo. So in this demo, we have a notebook that carries out ETL and ML in a single notebook, end to end, with and without GPU acceleration over Spark 4 Connect. And the notebook's adapted from one that is in one of our team's repos that has a collection of examples for accelerated Spark. This particular one involves a data set that is published by Fannie Mae involving mortgage performance. And the original notebook had XGBoost for the ML part, and in this demo, we're replacing that by our accelerated logistic regression, which is part of our plugin. That said, XGBoost can also, as it turns out, be run over Spark Connect. And there's actually a talk by some of our NVIDIA colleagues later today explaining how that can be done. But in this demo, we're using logistic regression. So the demo was run on, the client side was run on a laptop that was connected to a workstation with an RTX A6000 graphics card with 16 CPU cores for the CPU part. and we'll show where that connection happens. These two blocks here briefly show, kind of sketch out the ETL part and the ML part. The ETL part has 5 steps that do some feature normalization, determine the label, which is a multi-class label that specifies the degree to which, or by how many months, a mortgage is delinquent. And the ML task is to predict that degree of delinquency from the features. And then the third step involves extracting some information about the origin of the loans. Then everything gets joined, and the final step is to convert some string features to numerical indices. The ML part does a train test split on the output of the ETL part, and then runs a pipeline consisting of a sparse feature hasher, vector assembler, and sparse logistic multi-class logistic regression. And then finally, the pipeline fit method is invoked, triggering that whole cascade of operations. So at this point, I'm going to switch over to this other laptop, because it's easier to show the video of our demo. Okay, so let's see if this works. Okay. All right, so I've got some, let me just start the video, and then I'll bouncing back and forth between that dock. Okay, so here is the notebook, and the video is running. You can let me just pause it real quick. So at the top, by the way, feel free to chime in at any point, Gara. So at the top, we've got 2 flags that toggle some behavior of the notebook. So the first one is an accelerate on GPU. This one actually, the only thing this does is identify which run is GPU or CPU for purposes of logging the runtime at the end of the notebook. It doesn't actually affect what gets executed in the core part. And then the second flag optionally turns on or off the conversion from the original data set, which is CSV, to Parquet. But we're in this demo, we're starting from Parquet. So let me jump to, just move this over a little bit, jump to, oops.
So I think the flag also activates the ML backend classes in the connect session.
Okay. So here's the first key point in the notebook. At the bottom, we see that the line that actually establishes the connection to the remote Spark Connect server, like we saw in the short snippets earlier in the slide. The next key step is at the 1 minute mark, so we'll fast forward there, where we are setting up an SSH tunnel. You can see kind of, on the sort of bottom of the terminal window here, from the laptop to the workstation where the Spark Connect server is running. And there's the famous 15002 port for the Spark Connect server. And then we also tunnel into the Spark UI. Okay, so let's scroll forward to this point here, where we are starting up the CPU run. Oh, sorry, the CPU cluster, correct?
Yeah.
And it turned out that we had, previous to that, there was a GPU cluster, GPU-based Spark Connect server running. And you can see this display here at the bottom right, which is a program called NVTop that shows GPU, memory, and compute utilization. And you can see that just as the CPU base server, so previous GPU server is terminated and the CPU one starts, you can see the GPU activity going to 0. Okay, so we'll let that run a little bit. Now you can see the logging from the CPU Spark Connect server, and now it's kind of just hanging out there waiting. Okay, so the next key point, I will move forward, is at, so we've executed the cell that connects to the server, and now we're going to start running cells, logic cells in the notebook. So the next interesting thing is this smoke test, where we're doing some very simple Spark DataFrame processing, just to make sure things are working. So the key thing to look at here is I guess we're...
We need to skip to the clamp.
Yeah, that's right. Well, okay, here we go. So you can see that little bit of SQL ran, and you can see that the physical plan here shows no sign of GPU operators. So yeah, that confirms that we're in CPU mode here. So let's see, the next interesting thing is at 2:55. Okay, so here, okay, yeah, so just the notebook starts at Parquet. And then there's we are taking a look at the data sizes here. So we have actually just kind of small snippets of the full data set. And here we're looking at the raw data set, which was the original CSV at 11 gig. And then the Parquet version of that is much smaller, with thanks to all the compression in Parquet. Okay, so let's move ahead to where we actually start executing the core ETL part, which is right about here. So we should soon see a lot of activity in the logging, which indicates all of the, the CPU ETL processing. Here are the definitions of the methods that carry out the steps that I had summarized earlier. How are we doing on time?
7 minutes.
Okay.
Left.
Yeah, so let me, with that, just skip ahead to where the ETL part is done for CPU. So that would be at right about here. Okay, so the ETL is completed for CPU, and it took about 99 seconds. Okay, so next interesting thing is when we start the CPU fit method for the ML part. So that's right here in this cell 26. You can see it's running. And that's going to run for a while. So we will not watch the whole thing. Instead, we will skip ahead to a little bit of logging that's interesting to look at. So specifically right here, we see a little bit of protobuf string representation of the ML command that got sent as part of the execution of this fit. You can see that in the upper right logging window. Okay, so let's skip ahead to 803, and then here we see a top of the JVM execution of the CPU part. We'll just let that run for a little bit. And right about here, the ETL part, the ML part for CPU is done. Okay, so let me now move over to just jump ahead to where we kick things off for the GPU run. We're running a little low on time here, so this is where we're changing that flag to GPU. And then we go ahead and kill the CPU server up on the right and start the GPU one, and we'll soon see some activity, hopefully. Okay, guess we're still moving. Okay, so I think I will,
4 minutes.
yeah, there we go. There's some GPU activity. And the Spark Connect server at this point is waiting. And we will jump ahead to when the ETL GPU part has been started. You can see a lot more activity on the GPU. Okay. And then we'll jump ahead to when so the ML part should start running soon. Yeah, there we go. We got to the pipeline fit for ML with GPU. And you can see activity happening again on the GPU. At some point, it's really going to shift in the high gear. Okay, there it goes, right there.
Python worker and QML.
What's that?
You can point out Python worker and QML login.
Oh, okay. Yeah, and then we can skip ahead to the, GPU activity is maximal at this point, and the ML part is done. So we can skip ahead to where we show the plot the acceleration, 4x for ETL, almost 3.5 for the ML part, and then just another representation. And that's it for the demo. We're kind of low on time. So let me switch back here and just move real quick to our conclusion slide. So we have some QR codes here for getting more information, and for the ETL plugin, the ML plugin, and this is a placeholder for where we're going to have a pointer to the open source version of the demo that I had showed, which isn't quite ready yet. And that concludes our talk. Thank you.